Good morning, everyone. My name is Manie. I am an associate research professor in King Abdulaziz City for Science and Technology in Riyadh. This is a public research organization. It's similar to a university. We have a number of research centers. One of them is called the National Center for Computer Technology and Applied Math. That's where I work, and there are other centers. We're mostly doing research, and we also support research from, we fund the research from local universities. My presentation today is about biomedical signal analysis using a modified S-transform. This is actually a form of application of time frequency analysis. I'm not sure if you're familiar with it, but it's a procedure to analyze signals in time and frequency. So I'm just using this procedure and applying it to a biomedical signal, namely the EKG signal. The contribution of this work is mainly like a modification that is introduced to an already existing transform. It's called the S-transform. And I will show you, I'll give you just a brief introduction on what that is and what we have done in this paper or in this work. So we come to the next slide. This is just to give you an idea about what I'm about to talk about. We have an introduction, and then we'll talk about the S-transform, and then what kind of modifications or changes that have been done in order to improve its performance. And then I will talk about I'll discuss some of the results. And finally, I will just sum up the main points with a summary and conclusion. So what is the S-transform? It's actually a time frequency analysis approach or a technique which is similar to the short time transfer. I'm not sure if you're familiar with it, but it's basically, you take a signal, which we called in this case x of t, and then it is calculated using a modified Gaussian window. The signal is shifted with time for the entire length of the signal, and then you end up with a representation in time and frequency of the test signal or the signal that you're trying to test or to analyze. The value of the window here is calculated in this following form. It's, of course, a function of time and frequency. The advantage in this case is that sigma f, which is a value that is used to calculate the frequency, is a function of f. If f is a frequency, so it will give you more control on the signal itself. So once the value of this window is substituted in the main expression that we have looked at before, you will end up with the final expression of the standard S-transform. Now, what is the point of all this? Now what we are doing is just trying to improve the performance of this technique. So this is done by some adjustment. We are using additional parameters here to see if the time frequency representation would be more appropriate and would be easier to analyze. Here we have a parameter which is gamma. This is also an additional parameter. This is used to control the frequency resolution by changing the window's width. Also, you have a number of scaling factors, alpha and beta. These are added to determine the width of the basis functions that is used to improve the localization. The scaling parameter R is also used as a fine tuning for a better energy concentration. So when these values are substituted in the window, you will end up with a more complicated expression, which we look at in this form. So the modified S transform looks more complicated than the original one. However, it is supposed to provide a better performance. This also reduces to the original expression if we make the values of alpha and beta and R equal to 1 and alpha is equal to 0. So the next thing is how do we test the performance of this estimator? We're using standard signals. One of them is a sinusoidal FM, meaning you start with a higher frequency, then the frequency goes lower, and then it goes higher again. This is just basically a test signal. This is what it looks like in the time frequency plane. The x-axis represents the samples, and the y-axis represents the frequency. So you notice at the top left-hand side, there's what's referred to as frequency leakage or smearing. This is not supposed to happen, so we're trying to get rid of that, make the signal more concentrated around the instantaneous frequency. So this is our result, which is more favorable because we have removed basically almost all of the spectral leakage or the frequency smearing. Now it is concentrated around the instantaneous frequency. As an additional test, also another signal, which is made up of two crossing chirps. This is the time domain representation. It's just the signal here. It's more obvious if we look at it in the time frequency plane. Again, you see at the top that with higher frequencies, we run into the same problem of spectral leakage. So you see the bottom is okay, but at the top you have what is also called frequency smearing. So we're trying to improve that. This is what happened with the modified approach. You have a much nicer representation and a more accurate one. So we're claiming, that our modification gave us some results. Now the next thing is how do we use that result in a practical application, such as biomedical signals or speech or seismic or any other field. This is an EKG signal that I think almost all of you are familiar with. This is called the QRS. And what we're doing here is taking a length of this signal, which is equal to 1,024 sample points, and analyzing this signal in time and frequency using the approach that we have just made up or just calculated. This is the result that we have, once we have an EKG, which is a practical signal rather than a test signal. You can see that at higher frequencies at the top, you don't have any leakage. It's still sharp, and the representation is uniform. So we're saying, this is a better result than the original one. So summary and conclusion, my presentation is basically very brief. So what we have done here is just an optimization of the windows width that was used in the original S transform. And this was accomplished by adding some additional parameters to change the Windows variance and ultimately to improve the estimator's performance. And we saw that the spectral leakage associated with this estimator was minimized, resulting in an improved time frequency distribution. And also signal processing people look for some desired features. These are like invertibility and phase information. So these are still preserved and they can still be used. And the resulting estimator, as we have seen, was used to analyze an EKG signal. And the result was favorable, I think. And that's basically it. You know, if you have any questions or something, I would be happy to answer any questions. Yeah. I'm sorry, maybe this is not your area because it's mostly time frequency analysis, but it is, you know, an application of that approach to biomedical signals. But I understand that, you know, because it's mathematics, I know most people are not really into signal processing. So I apologize about, you know, maybe boring you with the mathematics and with all this.
No, I don't think this is the case, and the audience, they are also on the same mining. So thank you very much, Dr. Almana. It was a nice presentation. I have just one question. So how did you improve the smearing?
Yeah, this is it. You see, with the smearing, we had added the parameters, and this parameter, we adjusted them using some values, and then now you have a different formula instead of the original one. And
yeah,
you would, of course, write, you know, you would implement it. It was implemented on a MATLAB program.
Okay.
Yeah, it was implemented in a MATLAB program. Yes.
Simulated, yeah.
Simulated, exactly. Yeah. It was simulated in a MATLAB program, and the result was observed, like I have shown you, you know, the plots and the time frequency. Yeah.
So, but on experiment side, did you experiment it? So.
It is an experimental side, you know.
No, I mean the hardware-wise. The smearing, is it only as through the MATLAB as simulation, or you include some other components in the hardware, like, for example, low-pass filter, high-pass filter, to reduce the noise or to reduce the smearing? This is what I mean.
Yeah, yes, exactly. Okay, I know what you mean. Unfortunately, you know, with time frequency analysis, it's not really, viable to use, you know, filters. They don't really work because you're actually calculating. Even if you clear the signal before you remove any noise, before you implement it, before you simulate it, you will still have the smearing. Why? Because it's associated with the way it's calculated, because it's associated with the formula. So you have to do something to the formula itself. How it is done, how it is calculated.
I see.
You have to change it, change the way it was done, and then maybe you will improve the results. This is what we're trying to do. We have improved it, not 100%, but maybe like 80, 90%.
It's good. 80, 90, it's excellent. Anybody has any questions? So, Doctor, thank you very much. I appreciate. And I'm sorry that I cannot introduce you in the beginning because I'm looking for the biography.
That's it's very brief.
And this is appreciation.
Thank you very much. Thank you very much.